Hey everybody, in this section today, we're going to talk about trapezoids and kites. Finally, this is the end of chapter 6. So I'm posting these notes online for you. You can fill these in as we go, or just listen and play along. But the last two types of shapes, quadrilaterals, that we're going to play with are called trapezoids and kites. You might have heard these before, especially in real life, you know what kites are, but let's actually translate them into geometry and all the cool things we can learn about them. Now, the one thing you have to know is that kites and trapezoids are not parallelograms. They are not. They're still quadrilaterals, but they're not parallelograms. All right. For example, let's start with a kite. Okay. Here's what a typical kite looks like in real life on the right. And then on the left, if we sort of like dissect it in terms of the shape and the diagonals, that's what we have. This is kite H, J, K, L. And the diagonals meet in the middle at point P. But a lot of times when we draw a kite, we don't draw it necessarily with the diagonals. It could be just something like this. But what makes a kite, and definitely not a parallelogram, is the fact that it has only two pairs of consecutive congruent sides, not opposite sides. And if you notice in this picture for kite ABCD, it's not AD and BC, not the opposite sides. That would make it a parallelogram, right? No, it's the consecutive sides. So as you see here, you have AB and AD. Those two consecutive sides next to each other are congruent. And also over here, BC and CD are also congruent, but not opposite. Again, that would be a parallelogram. So a kite has two pairs of congruent sides, but they're not opposite, they're consecutive. Okay, so what kind of cool things can we do with a kite? Well, once you do put in some diagonals, what do we notice? If I kind of turn my head sideways and I look at it, it looks like I can kind of do this with the diagonals. You ready? Looks like I can do this. Do you believe? Yeah, I think it is. And in fact, you'd be right. First theorem about a kite is that diagonals are perpendicular. Do you remember what other quadrilaterals had perpendicular diagonals? Right, rhombus and squares, rhombus and squares. So a kite is kind of a near cousin to that. The diagonals are also perpendicular. If you've ever flown a kite or built a kite, remember when you make those little T-bars, the T-bars have to be perpendicular, and they are in a kite. What else do we notice? We talked about the sides, and we said that these two consecutive sides are equal, and these two over here, consecutive sides are equal. What about the angles? Are all the angles congruent? No, that would make it a parallelogram, right? But I think there are some that are congruent. Let's see. I feel like, again, if I tilt my head, not A and C, but I believe that B and D are congruent. And they are. All kites have one pair of congruent opposite angles. Only one pair. Only one pair. And that's our next theorem. In a kite, there's only one pair of opposite angles that are congruent. Only one pair. Not both pairs, because again, that would be a parallelogram. Now, how about those other two angles? They're not congruent, right? Well, let's see. A and C are definitely not congruent, but do you notice what's happening to them that's not happening to B and C? Do you notice what diagonal AC is doing? AC is actually bisecting those angles. So those little blue pieces are congruent to each other. That doesn't happen with B and D. These two angles here are not congruent, and these two angles here are also not congruent. So interesting, ready? In a kite, one pair of opposite angles are congruent, and the other pair of opposite angles are bisected by the diagonal. Interesting. One pair is congruent, the other pair is bisected. All right, so on the bottom, diagonals are perpendicular in a kite. One pair of opposite angles are congruent, and the other pair are being bisected by the diagonal. Okay, what kind of questions could we see here? Let's play with this and see what we can do. All right, let me switch screens, and I can do this on my iPad screen. We can play with these together. All right, given this shape here, folks, in kite PQRS, as you see on the side, I know that PQR is 78, PQR. So this entire angle over here is 78 degrees, and TRS, this little one over here, is 59. Okay, first of all, one thing I can mark is that because he's a kite, I know the diagonals are perpendicular. So I'll put that right there too. That'll help us. Can you see which angles are congruent and which ones are bisected? Can you see? I think R and P are the congruent ones. And therefore, I'd say that Q and S are the ones being bisected. Okay, so let's use that knowledge. So if Q is being bisected, that means if the entire angle we said was 78 degrees, let's divide that by 2 because he's being bisected. That means this little piece is 39 and this little piece is 39. Awesome. Okay, we know we've got 90. We know that TRS is 59. Okay, question 2A. What is QRT? What is this little angle over here? Well, we know that the whole triangle there formed by QTR or QRT is 180. Then we have 39 plus the 90-degree right angle plus whatever QRT is. Let's just call it X. We know that adds up to 180. So when we solve for X, add everything together, move it on over, and what did you get? What did you get? Give you a second to try that out. Did you get 51? Me too. There you go. Good for you. 51 degrees. So we use the knowledge of the bisecting angles and the congruent angles to help us out, and the perpendicular diagonals. How about QPS? Let's look over here at QPS. So I'm way over here, basically the big angle P. That's kind of an interesting question. How can we find QPS? Now, QPS is congruent to R, but it's not bisected though. Well, can we find R? Because I bet if we find the whole R, or QRS, then I think we find QPS. Well, QRS was equal to the red dot, that was QRT, that was 51, plus the green angle that I marked, that was TRS. We got that from the given information, 59. So therefore, QRS, or all of angle R, is 110. So guess what? So is QPS. Because those are the two opposite congruent angles. Okay, last one. How about PSR? Can we find how much PSR is? That's the entire angle down here. Again, these are not congruent angles with angle Q or RQP, but he is being bisected. So what can we do? Well, I know that the green angle again, TRS, was 59. I know that this is a right angle. Can we find, therefore, part of angle S? If we subtract from 180 and all the triangle stuff, we'll find that that little purple dot here is 31 degrees. Do you see that? Because all three angles added up to 180. If that's 31, remember, this is the angle that's being bisected, right? It's not congruent, but it's being bisected. So if that's 31, do you agree that the one over here is also 31? I'm going to tell you right now, folks, that the measure of angle PSR is 62 degrees. And I'll show you on my screen that we are exactly right. Shall we check? There we go. Do you see the answers on the bottom? Good job. Kites are pretty cool. Kites are neat, what we can do with them. All right, but what else can we play with? What if we play with another shape? How about a trapezoid? Trapezoid is the other quadrilateral that's also not a parallelogram. The reason why it's not a parallelogram is only one set of opposite sides are parallel. Only one pair, not both, only one. So here's our little trapezoid here. And if I mark the parallel sides, you can kind of actually see it, right? It's this one and this one, but not the other ones. The other two are not parallel. Again, if they were, we'd have a parallelogram, but we don't. Okay, well, the sides that are parallel, we're going to call those two the bases. So here's the top base and here's the bottom base. The bases are parallel. The parts that are not parallel, we call those the legs. So we have a leg here and a leg here. Okay, there's your trapezoid. One pair of parallel sides, they're called the bases, and the other two sides are called the legs. But now just be careful. Let's not always associate bases with top and bottom. They're not always on the top and bottom. And I can show you. Let me spin my trapezoid around a little bit so he looks more like this. Now look at this one. Is the base top and bottom? No, because they're not parallel. Can you see where the bases are now? Here they are on the left and the right. So bases should always be the two sides that are parallel, and the legs are the two that are not. Okay, well, do you remember in triangle land? In a triangle, if you have two congruent sides in a triangle, he's isosceles. Well, in a trapezoid, if your two legs are congruent, he's called isosceles. An isosceles trapezoid has two congruent legs. It would be back in this picture, this one and this one. Or up on top, this one, and this one. An isosceles trapezoid has congruent legs. The bases are not going to be congruent. If they are, then all the sides would be congruent, or at least the opposite ones, and we'd be back to parallelogram world. But we're not in a parallelogram world here now. All right. So a couple things that's cool about an isosceles triangle. Doop and boop. Again, here's my parallel sides, because he's a trapezoid. We could say a couple of things. If we broke this up into separate triangles and other things, we can prove a couple of neat things. And the one thing we can prove is in an isosceles trapezoid. Remember an isosceles triangle, if the two sides are congruent, the angles are congruent. In an isosceles trapezoid, if the two legs are congruent, then the base angles are congruent. Those two. But those aren't the only base angles. That means these are also congruent as well. But not all to each other. Again, he's not a parallelogram. These base angles. So an isosceles trapezoid, if the legs are congruent, then both pairs of base angles are congruent. That's a really good theorem here. Let's put that down. The base angles in isosceles trapezoid are congruent. So if congruent sides, then therefore congruent angle, and the other two as well. And basically the reason why the other two as well is we're going to use the fact of same side supplementary angles from the parallel lines. That's basically how we would prove that one. Now the cool thing is this theorem works if it's isosceles, then the base angles are congruent. We can actually say the converse. If you see a trapezoid that has congruent base angles, then he's going to be isosceles. It's sort of like the converse of the isosceles triangle theorem. This is the isosceles trapezoid theorem converse in a way. If the legs are congruent, base angles are congruent. If the base angles are congruent, then this is isosceles and the sides are congruent. So because the original and the converse are true, we can put it as one big, if you remember, biconditional. Isosceles trapezoid happens if and only if its base angles are congruent. Now, another cool thing, let's add diagonals here. Ready? Let's add a diagonal here. Oh, not very straight, Mr. Brown. And over here as well. Again, terrible diagonals. I'm so sorry. Looks like an Xbox. Cool thing. If it's just a regular trapezoid, these diagonals are just diagonals. They're not doing much. But if this is an isosceles trapezoid, would you believe it, if I do it better, that these two diagonals are congruent? And here it's written here as a biconditional. If it's an isosceles, the diagonals are congruent. If you've got a trapezoid with congruent diagonals, that trapezoid is isosceles. Absolutely true. Okay? So two great things about isosceles trapezoid. Both pairs of base angles are congruent and the diagonals are congruent. Yay. Let's play. Should we try a couple? Okay, let's try a couple of these problems. I'll put this on my other screen for you too. All right, so first thing you notice is when you get to these shapes and the trapezoids, are they isosceles or not? Okay, 3A here, friends. Let's just look at the shape before we're trying to figure out what we're doing. Let's see, I've got parallel, so trapezoid, and then congruent. So isosceles trapezoid, awesome. That means all of the base angles are congruent. This one's congruent to this one, and this one is congruent to this one. Great, okay. So the question is saying, what's the measure of angle F? Okay, well, if I know H is 49, do you believe that E is also 49? Yay, because base angles are congruent. Now, how can we go back up and do F and G? Like we said before, because they're same side supplementary with the parallel lines. So they both add to 180. So if this is 49 here, angle F or angle G should be 180 minus that, 180 minus 49. And if you do that on your calculator, 180 minus 49, you would get 131 degrees. There you go. So we use the fact that it's isosceles, so we have the base angles congruent, but also it's a trapezoid, parallel lines, so use same side supplementary. Okay, how about 3B? Now, if I know JN is 10.6, and NL is 14.8. Can I find KM? Well, that's kind of strange. KM is way over here. Huh. Well, it's like we kind of know parts of one diagonal. Can you find the other? Let's see what we got here. Well, we do have a trapezoid again. One pair of opposite sides are parallel, and he is isosceles. Yay! Remember, isosceles trapezoid, congruent diagonals. So both diagonals, JL is equal to KM. Can we find JL? We got both pieces and we add them together. If we add JN and NL, I would get 25.4. So how much is KM? Indeed, 25.4. You could see in the trapezoid, they're not bisected though. These diagonals are not bisecting each other. Remember, if they did, it'd be a parallelogram, but they're not. But isosceles trapezoid, the diagonals are definitely congruent. All right, one more, and this one's a good one. Can we find here the value of x so that this whole trapezoid is isosceles? So again, we know the opposite sides are parallel, so trapezoid. But know that because this is a trapezoid, we want it to be isosceles. You know, if I want this to be isosceles, that means the base angles are going to have to be congruent, right? So these two need to be congruent if I want this to be isosceles. Well, why don't we use that knowledge and why don't we set those two equal to each other and try to solve? Oh, a little bit of algebra here. How about one angle, 2x squared plus 19, has to be equal to the other angle? Okay, great. Let's solve. So let's try to get the x's by themselves on one side, and we'll toss all the numbers to the right side. So if I subtract 4x squared, I should get a negative 2x squared on this side. If I subtract 19 to the other side, I should get negative 32. All right, let's get that x by itself. We have to divide by negative 2 first. That's gone. Poof. Now I should get x squared equals a positive 16. Great. So therefore, x has two different things. We could say x is either equal to a positive 4 or x could be equal to a negative 4. But let's check, because remember we're in geometry, we can't have negative sides or negative angles. So we should always plug in our answers and see. Now, if it's a negative answer, that doesn't mean the angle or side's negative. So we should always plug in everything to make sure. Shall we do that? So let's plug in 4 into either one of these. And if you do it, I think it works out. 4 squared times 2 is 32 plus 19 is 51. And if we have 4 squared times 4 is 64 minus 13 is also 51. So 4 works. I like 4. And you'll see to verify, if you plug in negative 4, it will also work. You'll get positive sides and they'll be equal. So the answer to this question, once you set the angles equal to each other and solved, you get plus or minus 4. Good, folks. So that's how trapezoids work, especially if they're isosceles. Let's go back. Oh my gosh, there's so many more things we could do with a trapezoid. What else can we do? Let's see. Do you remember? Let's go back in time for a little bit. Do you remember when we had the isosceles triangles and we had what was called the mid-segment of a triangle way back in 5.4? Do you remember the segment that joins the midpoints of two sides? This over here. So if I had a point that was the midpoint of that side and a midpoint of that side, we called this friend the mid-segment. And the mid-segment was two things. First of all, we noticed that he was parallel to the third side, parallel to the base. And that looks like it too, right? The other thing we noticed is how long was it? Do you remember? The length of the mid-segment was half of the third side too, right? So if we know how long the third side is, if it was say 20, we know the mid-segment is 10, half of that. You know what? We can actually draw a mid-segment in a trapezoid. Check this out. So what I'm going to do is I'm going to take a trapezoid here. I'm going to draw a mid-segment here right in the middle. Oops. And it's a mid-segment, which means he is going to connect the opposite midpoints. So here's a midpoint here, and here's a midpoint here. So those two pieces are congruent, and these two pieces are congruent. Let me get rid of this extra little twig here that's growing out of my trapezoid. There we go. So we call this a mid-segment. This is the mid-segment trapezoid. Can you notice if we go back to the triangle one, can we talk about that thing being parallel to something? And it actually is. This mid-segment in a trapezoid is always parallel. But to what? Yeah, the bottom, you got it. But do you notice it's also parallel to the top? Not just visually, but because it's a trapezoid. Remember a trapezoid, the bases are parallel. And if the mid-segment is parallel to one of them, he's parallel to both of them. So the mid-segment of a trapezoid is parallel to both bases. And again, it looks like it too, right? The other thing, let's talk about length. Well, let me give you an example, and I wonder if you guys can figure it out. If I know this side had a length of 2, and this is a side length on the bottom of 8, I'm going to tell you right now, the length of the midsegment is 5. Do you know how I got that? Basically, what you do is you add the opposite bases and you divide by 2. We say that the length of the midsegment is the average of the two bases. So 2 plus 8 divided by 2. Another thing that's kind of cool, if you notice here, is that if it is really the average of the bases, do you notice that the distance I travel from one base to the midsegment is the same distance I travel from the midsegment to the other base? I travel here by 3. That works. That's not a coincidence. That's kind of cool. So it's kind of neat that works out for that way. And we can do different ways. We can say, instead of giving you 2 and 8, what if I know this is 5 on the top? And what if I say this is 15? If I know the midsegment is 15, now we can set up a whole algebra equation and try to say, okay, the average of the bases is 15 and try to solve for x. But can we use that little shortcut that we just saw? Remember, the midsegment is the same distance away from both bases. So if I know that 5 to 15 is plus 10, then to get from the midsegment to the last base, I'm going to do plus 10. So therefore, can you see that the last base would be 25? Let's double check that. Ready? Let's actually use the real definition. Ready? Let's take the average of the two bases. 5 plus 25 is 30. What's the average of those two? Divide by 2, and you get 15. Isn't that cool? Works out really, really well. Let's try one more. Okay, so let's put a little bit more algebra into it. I'll put this on my other screen so I can play with you with this one. Okay, on this one, here's our trapezoid. Let's label some things here. We got parallel, parallel. We have midpoint and midpoint, which means you can see obviously the 7s and the 6s are congruent. So that tells us that those are midpoints, which tells us this side in the middle is the mid segment. So I put that he's parallel to the bases, the 2x minus 4 and the x minus 3. And now let's try to solve for x. If we know that 10 is the mid segment, this is going to take some algebra. Ready? Okay, let's actually say the average of the bases, right? That would be x minus 3 plus the other base, 2x minus 4. Okay, the average, that means I'm going to add those two and divide by 2. That should be equal to the mid segment. And we know what that's equal to, right? That's equal to 10. All right, should we play at the top a little bit? That's x minus 3. And I can distribute the plus. It doesn't do much. And if we keep playing with the numerator there, let's gather some like terms. The x's, how about 3x? And the numbers, we get minus 7 over 2 equals 10. All right, I'm going to get rid of that fraction. You know, in order to get that x by itself, I'm going to multiply both sides by 2 to get rid of that denominator. Therefore, the 2's cancel. See ya. And you get 3x minus 7 equals 10 times 2. Awesome. Okay, well, we add 7 to both sides. 3x equals 27. And then if we divide both sides by 3, x equals 9. Okay, that's great. But with algebra, always, let's just go back and plug in our answer and see if it makes sense, just to see how awesome we are. Okay, if x is really 9, this would be 9 minus 3, 6. This would be 2 times 9 minus 4. That's 18 minus 5. That's 14. Okay. All right, let's check and see. 6 plus 14 divided by 2, that's 20 divided by 2 is 10. Yay, we got it right. X is equal to 9. Not only that, but can you see the distance from 6 to 10 is the same from 10 to 14. There you go, folks. There's a great, great introduction to trapezoids and kites. Kites are pretty neat, but as you see, trapezoids are much more complex and lots of things with it. So I'm posting these notes on RadarNet for you. You can film as we go, and we'll get a chance to play with these when we see each other next time. Good job today, folks. Have a really good day. See ya.